Hello, everyone. Welcome to the distinguished lecturer webinar, Near-in-Sensor Computing for Neuromorphic Machine Vision, organized by the IEEE EDS BUET SB chapter. I am Ankon Ghosh Dostidar, a fourth-year undergraduate student of the Department of Electrical and Electronic Engineering, and the treasurer of IEEE EDS BUET SB chapter. IEEE EDS BUET SB always tries to create a platform where the researchers, students, and interested ones from the related fields can engage and share ideas. For that purpose, we have planned to organize a series of distinguished lecturer webinar series, starting with today's session. For the very first webinar of this series, we are glad to have with us Dr. Yang Chai from Hong Kong Polytechnic University. I would like to welcome Dr. Chai, and before I'm handing the session over to our honorable speaker, I would like to share a few words with the audience. Please note that the session is being recorded, so if you don't want your video to appear on screen, please turn it off. I would also like to request you all to keep yourself muted during the session talk so that we can hear the speaker properly. If you have any questions, feel free to put them in the chat box anytime. I shall be sharing them with Dr. Chai from time to time. We will also be having a separate question answer session at the end. So now with my pleasure, I shall be sharing a few words about Dr. Yang Chai. Dr. Chai has been an associate professor in the Department of Applied Physics, Hong Kong Polytechnic University. He is the Vice President of Physical Society of Hong Kong, a member of the Hong Kong Young Academy of Sciences, the IEEE Distinguished Lecturer since 2016, and he was the chair of IEEE ED's SSC Hong Kong chapter for the 2017 to 19 timeline. He is a recipient of the RGC Early Career Award in 2014, the Semiconductor Science and Technology Early Career Research Award in 2017, PolyU First Faculty Award in Research and Scholar Activities in 2018-19, Young Scientist Award of ICON 2D Math in 2019, PolyU President's Award in Research and Scholar Activities in 1920, and NR45 Young Innovators Award in 2021. His current research interests mainly focuses on emerging electronic devices. So with that all, I will now handing the session over to Dr. Chai. Welcome, Dr. Chai, and thank you so much for joining us today.
Thank you very much. So let me share my PPT slides. So can you see my PPT slides?
Yes, it is visible.
Okay. Probably let me turn off the video to save some bandwidth. Okay.
Sure, no problem.
Okay, it's really my great pleasure to interact with IEEE student members in Bangladesh chapter. So the topic I'm going to talk about today is near-sensor and in-sensor computing for neuromorphic machine vision. So let's begin a big picture. So we are living in the Internet of Things, so there are a lot of data. In addition to this data, in our physical world, every second it generates a huge data. So every second it generates 10 to 34 bits. And with the development of Internet of Things, it will generate additional data. So by 2032, the number of sensors will be up to 45 trillion. And every second it will generate 10 to 20 bits. So this is very huge. It keeps increase every year. But for our human person, the sensory capability actually is very limited. For our human person, we can only sense 10 to 17 bits per second. It doesn't increase over in the past 1,000 years, 10,000 years. Our human person, the sensing capability, it doesn't increase. So that means we lost a lot of information from the environment. But our human person can still survive very well in the environment. So what's the reason? The reason is that for our human person, we have a lot of sensory organ, eye and ear. So this sensor organ, they are not only sensor. Actually, they also have a computing function. So when we receive some information from external environment, we only extract the useful information and then pass to our human brain. So in this case, our human person, for example, our human eye, actually it can reduce a lot of redundant data. The data compression ratio could be up to 10⁵ over 1. So the message I want to deliver here is that our sensory organ, they are not only sensor, they are also computing device. Okay, so let's go back to the conventional sensory computing architecture. So in conventional computing architecture, actually we have a lot of sensors. So this sensor typically collect some data from external environment. The data is usually analog. Then we have to convert this data from analog form to digital form and store this data in memory, and then we do some processing unit. So this parallel diagram actually works very well in the past years. But today we have a lot of challenge. The first challenge is we have many sensors right now. The number of sensors keep increasing. So it generates a lot of data, and most of the data are actually redundant. That means they are useless. The second challenge is the sensing device is typically analog, but the computing device, they are typically digital. So this sensing and computing device, they are physically separated in a whole system. So we have to transfer the data from here to there. It will cause additional power consumption and time delay. And also we have to do the analog to digital conversion and the digital to analog conversion. Again, it causes time delay and power consumption. So this challenge we have to seek some new computing paradigm to solve this problem. So here we propose some new computing paradigm, especially for sensor. That is near sensor and in-sensor computing. So we can shift part of the computing work close to the sensory terminal, either near sensor or inside sensor. So what is near sensor? Near sensor computing architecture, it still rely on the existing technology. So sensor is sensor, computing is computing, but we try to minimize the distance between the sensor and the computing. We can use some advanced microfabrication technology, for example, 3D monolithic integration, and we can also use advanced packaging technology, for example, chip-to-chip interconnect or die-to-die interconnect, to minimize the distance between the sensor and the computing unit. That is near sensor computing. So what is in-sensor computing? In-sensor computing actually, it requires the device has a double function. That means one device, it works as both sensor and computing. So for example, here we have many sensors. These sensors, they connect together. They can receive the signal from external environment, and they also form a neural network together. So this neural network can work together and do some simple computing task. Okay, from our in sensory computing, we have a low-level computing function and also high-level computing function. So what is low level? Low level actually is the input signal is still sensor signal. The output signal is also sensory signal, but their signal to noise ratio is increased, and the feature is more obvious for us to extract. So what is high-level computing? High-level computing actually is allow us to do more abstract representation. For example, we can classify image, we can recognize some pattern, and we can localize the sound. So we can know what and where of the input signal. So this is more abstract compared with the low-level computing. So in this talk, I mainly focus on the vision, because vision is the dominant way for a human person to collect information from external environment. Over 80% information are actually from the image or video. And around 10% the information are from the audio. Okay, so from the image sensor, actually, they also have challenges. Today, the resolution of the camera is much higher and higher, and the frame rate is also higher and high. So it generates a lot of data. And also the sensor and the computing unit, they are physically separated, and we have to do the analog and the digital conversion. But for our human person, our human eye, actually, it will be more efficient. Because for our human eye, I already state just now, it is not only a sensing device, it is also a computing device. So when our human eye receives a signal, actually it can pre-process the signal, remove some redundant data, and then pass the useful information into human brain. So vision begins with our eye, but takes place in our human brain. So because of this different working principle from the conventional electrical device, people try to study the working mechanism of human eye and try to emulate with a microelectronic device. For example, around 30 years ago, people already started this work in California Institute of Technology, carbon meter. They use the silicon CMOS technology to construct the circuit to emulate the function of the human eye. And in Japan, people also use the image processor. They use different material system, gallium arsenide, to construct a neural network to do the image recognition. So this area keep developing. So with the advanced manufacturing technology, the transistor is smaller and smaller, so we can build some complete circuit right beside the sensor. Then we can do the image processing. So we have a dynamic vision sensor, we have active pixel vision sensor. But most of them can only do a very limited processing. If we need to do some complicated processing, we still need to pass this data to computing unit and then do the processing. So in this case, we are trying to use some new hardware, emerging hardware to this hardware. It has the function of both sensor and some pre-processing function that allow us to do low-level and high-level neuromorphic vision processing. So first, let me talk about low-level neuromorphic vision processing. Low-level actually processing is just make the signal is more obvious, so we can enhance the signal to noise ratio. So motivated by this idea, we design a new device that is so-called Optoelectronic RRAM. We call it ORRAM. So what is the difference between the ORRAM as a typically image sensor? From the typical image sensor, it is a pin diode, so it's a reverse biased. So when light comes in, it will produce some photocurrent. So through this photocurrent, actually we can store information. But after we remove this light, the photocurrent will drop dramatically. No information can be stored. So here we try to use the ORRAM. In this ORRAM, with the light coming in, it generates the current. So even after the removed current, so we can still retain the device in relatively low resistance. Then we can store the information. So depends on the light intensity and the light dosage. Actually, we can change the conductance of this ORRAM. So in this way, we can do some pre-processing function to make the signal more obvious. So when we try to fabricate device, we start to there are a lot of choice. There are a lot of choice that has optoelectronic response. So light coming in, it will generate photocurrent. Many semiconductors have this function. But in our work, we choose a transition metal oxide. More specifically, we choose the molybdenum trioxide. So this oxide, it is a typical photochromic material. So here you can see, when we deposit this molybdenum trioxide, it looks transparent. But if we use UV light to do the light illumination, the color of this oxide is converted from transparent to the dark blue. So depending on the light intensity, the color could be different. So people already use this property from some smart window. But when I look at this phenomenon, when the color is changed, that means the optical absorption is changed. The optical absorption is changed. That means the band gap of this material is changed. If the band gap is changed, that means the resistance could be changed. If the resistance is changed, that means we can use the resistance to store the information. So the mechanism is not very new, but we use this mechanism for the information storage. So in this way, I ask my student to design very simple two-terminal structure, just like a capacitor. The bottom electrode is a PD, and the top electrode is ITO. This is transparent, allow the light go through. So the switching material is a photochromic material, MO3. So here you can see when the before the light illumination, the device is in high resistance state, but after the UV light, the resistance is reduced. When we apply a reverse voltage bias, it can change back to the high resistance state. So this device still can work for many cycles. So as I said, the switching mechanism actually is associated with the valence state change of molybdenum ion. So from the as deposited, it is transparent, in which the molybdenum it has the valence state of 6. But after the light stimulation, the color is changed to blue or even to dark blue, depending on the light dosage. So part of the molybdenum actually is changed to the valence state of 5. So from the valence state of 5 of MO, it is more like a metallic state. So the conductance is dramatically increased. So according to the light dosage, actually we can change the synaptic plasticity of this memory cell. We can let it to be the long term. We can let it to be short term. So so more specifically, we can change the light intensity. We can change the the power savance of this light stimulation. So here you can see this is a short-term plasticity. We can control through this power savance also the light intensity. But if we increase the light intensity of the power savance, so this memory cell can be changed to the long-term plasticity. So here you can see with the increase of the light intensity, the current density is increased as well, and it becomes non-volatile behavior. So this light intensity dependent characteristics allow us to do the image pre-processing. So if we are going to process the relatively large-scale image, we have to do prepare array. So in our university clean room, we prepare a relatively small array. This array just consists of 8 by 8 cell. So from here you can see, so each white dot is a pixel. So we can use a different lighting intensity to represent the image feature. We have an optical mask, and then we do the light stimulation. So here you can see, if the lighting intensity is relatively strong, we can get the memory effect is more obvious. But if the lighting intensity is relatively low, we can still record the feature, but the memory effect, the contrast is not that good. If the lighting intensity is further reduced, it will be not non-volatile behavior. It will be changed to one type. The image will be not recorded. So based on this light dosage dependent characteristics, actually we can do some basic pre-processing function. So here you can see we choose another array that is 3 by 5 array. So when we do the light illumination, so if the light intensity is relatively low, it will be automatically filtered as a noise. If the lighting intensity is relatively strong, it will be recorded. So through this self-adaptation process, the output image will have the relatively high image contrast. So here we don't need to use any some circuit or algorithm. So we just use the ORRAM sensor. We can realize this function. So to do more complicated image processing, we have to rely on relatively complicated neural network. So here we can use a RRAM to construct a neural network. So after the ORRAM do the pre-processing, then we input the image to the RRAM array. So because our array scale is relatively small, we cannot process complicated MNIST database. So here we construct a database by ourselves. So we can generate the noise by some randomly. And after the ORRAM pre-processing, the contrast is better. And then we use the neural network to do the image recognition. The recognition rate and recognition efficiency is much better compare the case without the ORRAM pre-processing. Okay, so this is just a low-level vision processing. The input signal is a sensor signal. The output signal is still sensor signal. But through this pre-processing, the signal-to-noise ratio is better. But for the vision processing, sometimes we also need to do the high-level processing. So here I can show you another work. This work is not reported by myself. This is by Thomson Muller. This work is published last year in Nature. So in this work, they use WSE2 as a photosensitive material. So they construct a double gate phototransistor structure. So here you can see one gate is applied positive voltage, the other gate is applied with negative voltage. So in this way, this WSE2 actually can form a PN diode. So when the light go inside, it will convert the light into some electronic signal. So here they have 1 pixel. They have three WSE2 photodiodes, but their polarity can be changed by the gate voltage. So in this way, they connected these 3 transistors in parallel. So the output current will be the sum of from these 3 individual phototransistors. Then this transistor is not only size. They further construct with other transistors together form a neural network. This scale of the neural network is relatively small. It's just 3 by 3, but it allows us to do some very simple computing function. Okay, so with this photosensor neural network, so they can do the supervised learning, realize the function like classifier. They can get recognize some later. They can also do the unsupervised learning algorithm. So they can extract the initial feature from the input signals. Because this architecture, the device is both sensor and computing unit. They don't need to transmit the data from sensor to computing unit. In this way, the speed is very, very high. They demonstrated the processing speed is as low as a nanosecond. So I'm one of the review of this manuscript. So after this paper is accepted, the editor of Nature asked me to write a view. So in this article, I first proposed the concept of in-sensor computing. So what is in-sensor computing? People are very familiar with the in-memory computing. For the in-memory computing, actually, we do the multiplication through the Ohm's law. So when the voltage is applied to a RRAM, then you can change its conductance. So resistance time the voltage, then you can get voltage divided by resistance, then you can get the current. So that is a typical multiplication process. But for the in-sensor computing, this is different. So here, the current actually is the product of the responsivity and the external stimulation. So, but from the responsivity, actually we can change it. So that is works just like synapse ratio in the neural network, which can be changed by the gate voltage. So when the external stimulation comes inside, it will time with the responsivity, it will generate current. And then we can use the Kirchhoff current law to do the summation. So with this multiplication and summation, then we can do typical matrix operation. So the matrix operation is the basic operation from the neuromorphic computing. So here so how to realize the near-sensor and in-sensor computing architecture? For the near-sensor computing, we still rely on the existing processing technology. We just max the interconnect distance is shorter and shorter. But from the in-sensor computing architecture, actually we have to adopt some new material and new device structure. So this new device, they must have a multiple function. Work as both sensor and a computing unit. So from practical application, it seems near-sensor computing is more close to the practical application. So how to realize the near-sensor computing? So for example, through the microfabrication, actually we can realize a 3D monolithic integration. For example, the bottom layer, we can still use the silicon CMOS as the digital process. But for the memory, we can use oxide. The processing temperature is only around 100 degrees. And then we can use some sizer, but it requires the temperature must be, processing temperature must be very low. Also, we can rely on the existing packaging technology. For example, we can use a 2.5D chiplet integration. We can use existing matured chip that we can use an interposer. In the interposer, we can design the interconnect layout that we can place the chip on this interposer. But in this case, the interconnect length is very long. The performance is not that high. Okay, the last part from the neuromorphic vision sensor, we are going to demonstrate the vision adaptation. So what is vision adaptation? So vision adaptation actually, that is our human eye response when the external light condition is changed from the light to dark, from dark to light. It will take some time for our human eye to get the much better image quality. So here it is a Sootopic adaptation. So in the initial status, the background is dark, but when we go inside the very light condition, we cannot see nothing. But after a time that we do the adaptation, we can gradually see the image clear. So reversely, we also have a Photopic adaptation. That is, we go inside from the light to the dark room. So how to describe this adaptation process? We have Weber's law. So Weber's law, that is talking about the minimum increase of stimulation, which will produce a perceptible increase. Actually, this is a threshold. This threshold is proportional to the stimulation in last state. So if we use the schematic to describe the Weber's law, it looks like this. So here you can see the y-axis actually is the vision threshold. The x-axis is the light intensity. So if the background is dark, the vision threshold, it's also about the light intensity. Its vision threshold will be also low. But if the background is very bright, so the vision threshold will be also high. So in our human eye, its photoreceptor, it has two types. One is a cold cell, the other is a root cell. Cold cell, it only responds from the bright light stimulation. Root cell is only for dim light stimulation. So when we do the adaptation process, actually we have a horizontal cell. Horizontal cell, it can change switch between the number of the root cell and cold cell. So if we go from dark to bright background, so our horizontal cell will gradually shift the working region from cold cell to the root cell. So then we can get a much better image. So reverse, we also have for the Photopic adaptation. So we try to emulate this adapting process with some new devices. So here we use a two-dimensional layer, MOS2, and the phototransistor. Why we use a 2D MOS2? That is because its thickness is the atomic level. So when we do the electrostatic modulation, it will be very effective. And also because its carrier concentration is relatively low, or when we when the in the gate oxide there are some trapping state, we can easily do the modulation. So in this way, we can do we did the light intensity dependent the calculation. So here you can see if we apply the positive gate voltage and negative gate voltage, their photo response behavior will be totally different. So here we give the you can see if you apply the let's look at the figure D. So if we apply the positive gate voltage, the photo sensitivity actually is relatively low. But if we apply the negative gate voltage, the photosensitivity is relatively high. So in this way, we can use the gate terminal to control one device to have either high sensitivity or low sensitivity. So in this way, we can use one device to emulate the function of co-cell or root cell. Okay, so here we choose a form by form phototransistor array. We try to do the image capture. So without adapting process, that we don't apply any gate voltage. So here you can see the image contrast actually will be very bad. But when we selectively apply the gate voltage to the array, that means we have an adaptation process. Obviously, you can see the image contrast is much better. Okay, so we also do the more dynamic process to capture the image. So here you can see one is the Sootopic adaptation process and the other is the Photopic adaptation process. So through this adapting process, we can max the image contrast of the output image is much better. So then we can connect to the neural network. After the adaptation process, we connect the output image to the neural network. Then we can do the adapting process, and then we can recognize the image. From here, you can see the recognizer accuracy is very high. It's up to 96%. Okay, furthermore, we use MOS2, wafer scale MOS2 to construct 620 pixel MOS2 neuromorphic vision system. So not only use the phototransistor, we also construct some circuit like the in-sensor amplifier and anti-vanishing memory and ADC converter. All of these elements we construct from the MOS2 device. So here you can see we can demonstrate the machine vision and showing a much better image contrast. Okay, so it's already 40 minutes. I think I should stop here. Just a very quick summary. So there are a lot of data from the image sensor. So we have to change our conventional sensor computing paradigm to some emerging computing paradigm. So this area requires interdisciplinary research, including both material, device, circuit, algorithm, and a more complicated integration technology. So this is my founding support and my collaborator, Professor Philip Wang from Stanford, Professor Jingfen Kang from Peak University, also Shimen Yu from Georgia Tech. So that's all for my presentation. Thank you very much for your attention. So I'm happy to take a few questions.
Thank you very much, Dr. Chai, and for your nice and informative presentation. I can see more questions in the chat. So the question is like, can you please comment on the advantages of TMD-based phototransistors?
Can you please comment on the advantage of TMD-based phototransistor? Yes, this is a very good question. So there are few advantages of two-dimensional TMD phototransistor. The first advantage, as I said, its thickness, its channel thickness is very thin. It's only a few nanometers. So here actually we use a double layer MOS2. It's just a 1 point. Its thickness is 1.4 nanometer. So in this case, if the channel thickness is very thin, we can do the electrostatic modulation more effectively. So we can apply very relatively low voltage, then we can dramatically change the photocurrent. And more specifically, the trapping state between the 2D semiconductor channel at the gate dielectrics, there are some unavoidable trapping state. So in this trapping state, it can trap some carry. So the carry density inside this trapping state is comparable to the carry density inside the MOS2 channel. So in this case, we can make use of this trapping state to do the adaptation process. Because this trapping state, it will increase or decrease the photocount at a different gate voltage. We can make use of this phenomenon to emulate the adaptation process. So I think these are two most obvious advantage over conventional semiconductors. Yeah, I hope to answer your question.
Thank you. If any of you have any questions, feel free to ask. Now it is the question and answer session. So we have another question. Can you please also comment on effect of the color depth on the ORRAM?
Can you please also comment on the effect of color depths? Color depths of the ORRAM. What do you mean the color depths? Do you mean the wavelength dependent characteristics? So in this work, actually, we didn't do the wavelength dependent characterization because from the MO03, it is a wide bandgap oxide. So it limits us to choose different wavelengths to do the simulation. Here we have to use UV light because because bandgap is very wide. If you use visible light, the effect will be very weak. Actually, here we didn't we didn't study the wavelength dependent properties.
Thank you, Dr. Chai. I think since we are now at the question and answer session, you can just, if you have any questions, you can just unmute yourself and ask directly, or you can also put that in the chat. No problem. Jubair sir, do you want to add anything?
All right. Thank you, Dr. Chai, for your nice presentation. So, like, if you want, like, so for these experiments that you have done so far, is you have not done like if the image it has different colors, then you cannot detect in the output. In the output, you cannot detect that one, right, from the output of the ORRAM.
Yeah, I can see your point. So from the typical image sensor, actually we have three. We have three individual sensor. That is RGB, red,
RGB,
green, and blue. So, but from this kind of image sensor, we have a lens. We have a lens to direct different color to different image sensor. So here we still didn't reach that step because it will be system level, but our work is still device level. If we are going to develop this study to close to practical application, your question is certainly right. We have to consider the RGB effect. But right now, for ORRAM, we can only respond to the UV light.
So was there any like reason for why you have chosen ORRAM? You can use any other. Can you use any other like volatile, non-volatile memories?
Why we choose ORRAM? That is the first reason is the material system is relatively stable, so we can do the for students it's very easy for them to do the fabrication process. But I think this principle can be also extended to the visible regime, but we have to choose a different material system. Right now, I have a postdoc who is trying to change some material system with a narrow band gap to respond to different light. But this work is still ongoing.
Okay, thank you. The audience, if you have any question, the floor is open for question.
You can ask your question. You can unmute yourself and ask your questions. You can also put that in the chat. Okay, so I think we can move to the concluding part. If you have any questions, meanwhile, I think you can unmute yourself and or put that in the chat. Before that, meantime, we can take a group photo with our honorable speaker. So I would like to request everyone, if it is okay for you, to turn on your video, and we will be having a group picture. Okay. Okay. You can turn on your video so that we can have group image with our honorable speaker. Okay. I'll wait for a few more seconds and then I will take the photo. Okay, so I'm taking the photo. Let me take another one. Ready? Thank you. It is taken.
Thank you.
Okay, so let me share my screen for a few minutes. So again, Dr. Yangche, thank you so much for such a wonderful talk. We really learned a lot of things, and it is really all the things are happening recently. So it is about the recent things, and thank you so much. So we just want to share a token of appreciation with you, and thank you again for delivering a DL talk, and hopefully we shall meet again with any other program with IEEE DS BUET SP chapter.
Thank you very much. It's my great pleasure. Thank you.
Thank you, Dr. Chai, for delivering this very interesting and recent, actually, some very recent, hot topic kind of work. So, like, we appreciate your talk, and hopefully the audience who have been present here, they have learned a lot of things, and hopefully whenever the pandemic is over, we will be able to invite you in Bangladesh sometime in some conference or from the chapter. Okay, thank you.
Thank you. I also hope to visit.
Yeah, it was really great to have you with us. So if we don't have any questions, I think we can now conclude our talk for today.
All right, thank you.
Okay, thank you.
Thank you everyone, and special thanks to again our honorable speaker, Dr. Yang Chai.
Okay, thank you.
Yeah, and thanks.
Bye.
Okay, goodbye, and thanks to the participants for joining. Stay safe. Goodbye.
Goodbye.